Okay, let's get started. So today we will continue with logistic regression. Talk a little bit more about project number 3. And I will let you know most likely right after class if the project is shortened and all, depending upon how far we get here today. Are there any questions before we begin? Okay, last time was the first time we talked about logistic regression. Logistic regression is used in a particular situations where we have where we want to predict one of two different groups for a particular observation. And typically we allow these groups to be denoted by y equals 0 and y equals 1, where 0 is often phrased as a failure, 1 is a success. And that obviously matches what we have with our place kicking data as well. And so this is one way to represent our logistic regression model, where pi represents the probability that y is equal to 1. So the probability of a success. And we set pi equal to the exponential function evaluated at a linear combination of regression parameters, these betas, and these x's, which are our independent variables. All that divided by 1 plus that e raised to the linear combination again. Okay? Another way to represent this model is like this, where we just use some math so that we just get this linear combination of the betas and the x's on the right side, and we are left with here the log of pi over 1 minus pi. People often do a little shortcut notation with this and say that this is the logit of pi. Just out of curiosity, because I don't think we really talked about this last time, this pi over 1 minus pi, this is essentially the probability of a success, or y equal 1, over the probability of a failure, y equals 0. What's another word to represent this kind of a ratio here? Does anyone know? It's actually an odds. So this is the odds of a success here. And so people often, so notice we're modeling the log odds of success is equal to this linear combination of the betas and the x's. And because of that, when one tries to interpret a logistic regression model, which really isn't our purpose here, that would be the purpose of like Stat 875. When one tries to interpret, let's say, the effect that x1 has on your response variable, your dependent variable, people will often use odds ratios, where you take the ratio of two different odds in the end. Okay. So we left off just starting to talk about the place kicking data example. Our ultimate goal will be to try to predict, should this be a success? Should this be a failure? Right now we're just looking at just enough of we're trying to get just enough background on logistic regression so that we can eventually get to that later today. And so if you remember, this is the model that we're actually interested in here. So the log of the odds of success is equal to this linear combination of the betas with the independent variables. So we have week, we have distance, we have wind, and so on. And we end up using the GLM function to actually estimate this model. The syntax for this function is very similar to what you saw with the LM. The main difference is that we have this family argument here, which just allows us to say, hey, I want a logistic regression model. There's many other kinds of models you can actually estimate with the GLM function, so that's why we have to specify this. And we saw how if you put the results into mod.fit, and you just type mod.fit at a command prompt, you get your beta hats. And you can think of these as coefficients on then these x's are independent variables in our model. That's why it's called coefficients here. And so we can actually write out our model. One thing to be very, very careful about, because I am picky when it comes to this, this is now our estimated model. And since this is an estimated model, we have to put a hat on top of pi to say, hey, this is an estimated quantity, rather than this model here would represent, let's say, for the population of all place kicks out there. Okay, so that's where we left off. Now, the stuff that's in mod, there's a lot more stuff in mod.fit than what we just saw. And mod.fit is actually a list. And so if I say names mod.fit, I see a listing of all the different components of what's inside of mod.fit. In particular, there's one called coefficients. So if I say mod.fit $coefficients, I get all those beta hats again. Now, as with any object in R, it also has a class associated with it. In this case, actually, it's two different classes. One called GLM, which happens to be the name of the function, but when you construct one of these functions, you don't have to make the class the same name as the function, but that's typically what's often done. And also has another class, LM. Okay. And so if I do methods class equal GLM, I see a listing of all the method functions associated with this class. In particular, we are going to use one very shortly called predict. And that's going to allow us to get a prediction for what pi is. So it's going to give us our pi hats. It works very similar to how predict works with when you're working with LM function. And another one that we're going to be looking at very shortly too is summary. And just like how you saw with the LM function way early in the semester, this is going to summarize the information that's inside of mod.fit. Now again, there's a second class associated with this as well as LM. And you're going to notice some similar names here like predict and summary. Now the way that R actually chooses a particular function to run, if you say, let's say summary parentheses mod.fit end parentheses, it goes to GLM first to look to see is there a particular function. So it executes that first. Okay. And so here is the summary of mod.fit. This summary is very similar to what we saw with a regular old regression model. The main thing that we will focus on in this class is the coefficients table. So for example here, this is beta hat 8. So the coefficient in the model, or the corresponding beta hat in the model for wind, is negative 0.63. Then we have a STD period error column. This corresponds to standard errors, and that's just a fancy name in statistics that we use for the square root of the estimated variance of beta hat. Okay. The z-value is a test statistics that is used to do the following hypothesis tests. HO is beta 8 is equal to 0. HA is beta 8 does not equal 0. And my z test statistic, let's call it z0, is negative 1.83. Where does that come from? That is beta hat 8 minus a hypothesized value of beta, which is 0, all over that standard error. Okay, very similar to what you would have with regular old regression analysis. So my test statistic is negative 1.8. Now, as you might expect, since we're using z here, we're going to use a standard normal approximation. So here's my standard normal distribution centered at 0. And if I use, let's say, alpha of 0.05, and this should be familiar, I have negative 1.96 here, I have positive 1.96 here. We see that my test statistic of negative 1.83 falls right about there, so it's close to that borderline for rejection. And in fact, if I were to use, let's say, alpha of 0.1 instead, I would have, let's say, negative 1.65 here and positive 1.65 there. And we can see that it is outside the rejection region. And so because of this, we say we have marginal evidence that beta 8 does not equal 0. It's not strong. We have marginal evidence. And that suggests that there's marginal evidence then that wind is important. So if we look at all these, and also we could do a p-value. So this p-value here is, remember what a p-value is? It's just a measurement of how extreme you are expressed as a probability relative to the probability distribution. So this p-value is calculated much like any other two-tailed test p-value that you've seen in the past. If I have a standard normal random variable z, I'm looking at the probability that it is greater than the absolute value of negative 1.83. And I take it times 2 because it's a two-tailed test. So the p-value is 0.0668. Again, marginal evidence that indeed wind is important. Is everyone comfortable with that? I mean, it's the same kind of interpretation that you would have with doing regular regression models that you would have in SET 801. Just as a different model. So, over here, overall though, what variables are important? Which ones? Look at the p-values. So we're looking for low p-values. So distance is important. And I'm sorry, what was the other ones? PAT. Any other ones that might be marginally important? Excuse me? Well, wind and change. Okay. Okay. So what we just did here is what's called a Wald test, named after a person who came up with the idea, Wald. And Wald tests are used widely in statistics whenever you're using maximum likelihood estimation. The reason being is because maximum likelihood estimates, generally speaking, if you think of them as statistics, they have a normal distribution associated with them. And notice how we were using a normal distribution. However, Wald tests don't always work the best at times. And so what typically is a little bit better is to use a likelihood ratio test. We talked about likelihood ratio tests in the factor analysis section, and we can do these likelihood ratio tests rather quickly. If we use a package in R called CAR, it doesn't stand for automobiles. It's actually CAR stands for Companion to Applied Regression. It's actually a book, and so it's a package that the authors of the book wrote. And if we use a function called ANOVA with our mod.fit return object, notice the capital A there. That is important, because R is case sensitive. We get likelihood ratio tests. I'll explain why it's called ANOVA shortly, because we're not doing ANOVA. And so we can see here, if we look back at wind again, for that same hypothesis test, negative 2 log what we would call delta for the likelihood ratio is 3.224. P-value is 0.07, and we get very similar results to what we did with the Wald test. Yeah, I would expect it in this particular case because we have a fairly large sample size. If the sample size was not large, you can see some greater differences with the two different hypothesis testing methods. Okay, so overall though, you can take a look at all the other p-values, we get similar results. So why is this called ANOVA? We are not actually doing analysis of variance here. The reason being is because some of the goals in analysis of variance are similar to here in terms of determining what factors, what variables are important. And so that's why this name has carried forward, even though we are not using ANOVA. Okay. So some comments. So if we go back up to here, to the summary mod.fit, remember our dependent variable, our response variable, is either a 0 for failure or 1 for success. And the way that this function GLM works, when you say I want logistic regression, and if you have values of 0 and 1 for your dependent variable, it will actually try to find a logistic regression model for the probability y is equal to 1, which in our notation then is pi. But why did it choose that versus maybe doing a model for the probability y is equal to 0? It all comes down to some stuff that we talked about in the discriminant analysis section. Remember, there is a particular way that R does an ordering to form indicator variables, where basically R orders the levels of a particular variable like this, 0, 1, 2, 9. Then, after the numbers, it does the letters. And R uses the set first level equal to 0, you could say, when it forms indicator variables. In this case, our levels are 0 and 1. 0 is the first level. And so because of that, then, if I were to, let's say, form an indicator variable for the good variable, that variable would be, well, for the level of 1 for good, that would be my 1. For the level of 0 for good, that would be my 0. Okay, I know that's maybe a little bit confusing. But let's say if we had instead a situation like this, where let's say good was a 1 for a failure and a 2 for success. What would R be actually estimating a model for? The probability y is equal to 2. Because it's the second level. If instead I had, let's say, levels of A and B for my dependent variable, what would R be trying to estimate a logistic regression model for? It would be for the probability y is equal to B. So it's important to know that. One reason why I bring this up is if by chance some of you have experience with SAS, SAS is the opposite. Unless you put a particular option in your code. Okay, yes. Yeah, so I mean, you could easily change the order of the variables in your data. I mean, of the variable levels in your data frame. Let's say if I wanted to, instead of having 0 and 1, let's say if I wanted to have 1 and 2. I could use the if-else function, which we've seen once or twice before, and say, well, and we'll see it again here, I think, today. If-else, let's say my level is equal to 0, then assign a value of 1. Otherwise, assign a value of 2. That would be one way to do it. Another way to do it that we've talked about the factor function in this class, but I don't remember if we've talked about it in this much of a detail. You can actually use the factor function to change the leveling as well in terms of the ordering. If you want more details, I can point you to another course that I teach that we would talk about that. Generally speaking, it's not going to be important for us to do here. But it's important for you to understand this ordering. Because especially for some of you, for your projects, you might not have a 0 and a 1 automatically for your 2 levels of your dependent variable. And you need to understand, well, what is GLM actually doing? And all comes down to is that the second level then corresponds to what R is trying to use for your, let's say, your pi, in terms of the probability. So like the probability y is equal to B is what R would be trying to model if you had levels of A and B for your dependent variable. Any questions about that? Obviously, it's very important because you don't want to be doing something the exact opposite of what you think is actually occurring. And it's not consistent across software packages. Yes?
How I change the default? I mean, it says the default to 1.
You would have to do one of the two things I just mentioned in terms of you need to actually use the if-else function or use the factor function to change the ordering. Okay?
Can you explain a little bit more about wall tests?
Sure. So wall tests, again, it's a common way to do hypothesis tests concerning a parameter whenever you're using maximum likelihood estimation. So like in a PhD level stat course for just PhD majors, one would actually learn how to do a mathematical proof such as this. We'll just call it C, where the square root of n times some maximum likelihood estimator theta hat. If you subtract off what you're trying to estimate theta, that converges in distribution to a normal random variable with mean 0 and some variance. Okay, that's a fancy way to put it. All this is saying is that for a large sample, your maximum likelihood estimator, if you think of it as an actual statistic rather than whatever the actual numerical value is, so a statistic can vary from one sample to another, it has a normal distribution to it. Generally speaking, there are exceptions. So because of that then, since I know what the distribution is, I have now a way to understand what would be an unusual value for theta hat, what would not be an unusual value. And that's why we can do a hypothesis test here. And so the basic idea is that, let's say if I just have theta, the Greek letter theta, that's my maximum likelihood estimator. If I subtract off some hypothesized value, let's call it theta 0, and I divide by the square root of the estimated variance of theta hat. And there are actually ways to calculate this without getting into all the details. Call that a test statistic of Z. Now I have a way to essentially standardize what this theta hat is. And I can compare it to a normal distribution. And, we know with a standardized normal distribution, 95% of all possible values of now, in this case, Z0, should be somewhere between negative 1.96 and positive 1.96. If I have something that's outside here, I know that that would be quite unusual if the null hypothesis was true. So therefore, I would say, let's say reject HO. If it's inside these two borderline values, I say, well, don't reject HO. Does that answer your question, or were you looking for something else? We can talk about more after class if you want to. Okay. But wall tests are widely used because they're so simple. It's just they're not always the best way to do hypothesis tests. Okay, so this is what our estimated logistic regression model is. So a simple question that I could ask on a test is, okay, go estimate the model, state it. And this is what you need to do. Again, you do need to put that hat there. So given this model, then what happens to the estimated probability of success as the distance increases? Does the estimated probability of success go down, or does it go up? Think about what you would do if it was just a regular regression model. How would you make that decision? You would look at what? Yeah, that beta hat. So it's negative. So that means as the distance goes up, what happens to the estimated probability of success? It goes down. Okay? Because of that negative coefficient. If you're not comfortable with making that judgment based upon that transformation that you have on the left side of the equation, all you need to do is, let's say, plug in two different values of distance. And let's say distance of 20, maybe you'll get here, let's say, and I'm just making these numbers up, 3. And a distance of 30, maybe you get 2. Okay. From that, how would you actually come up with the probability of success? Well, you would say e to the 3 over 1 plus e to the 3 for the 3, and then do something similar for the 2. You get the estimated probability of success, and then you can compare the two. Okay. So what happens to the estimate? And notice how this is intuitive as well. If you're a football fan, as the place kick gets longer and longer and longer, the chances of making the place kick should go down. What happens to the estimated probability of success for lead change as opposed to non-lead change place kicks? Again, we take a look at that. So we have a negative there. So for a lead change place kick, meaning that if the place kick is successful, it causes a different team to be winning the game. You might think there might be more pressure on that place kicker. And if there's more pressure, maybe the probability of success actually goes down. Since I have a negative coefficient here, indeed, that's what happens. But we need to be very careful, though.
Excuse me.
Yeah.
Can you say here, for example, the effect of change is more than distance?
No. It's because they're on different numerical scales. Distances in yards, let's say, change is either 0 or 1. Okay? So you can't just look at the beta hat alone. I think that's maybe what you were doing. Okay. But we have to be very careful about this statement that I just made about change. Notice the p-value from the likelihood ratio tests. There was only marginal evidence. And so, because of that, I have to be careful about how strong of a statement that I make there. Then indeed there's, let's say, a pressure effect. So if we take a look at, let's say, ELAP 30, notice its p-value. It's large. So I do not have sufficient evidence to say that ELAP 30 affects the probability of success. So that means if I look at this here, ELAP 30 has a positive value. And so I can't say, just because I see that positive value, that, as the lap 30 goes up, the probability of success goes up. I cannot say that at all. Because there's not sufficient evidence to say that if I were to take, let's say, another sample, I would get the same result. With distance, because that p-value is so small, I would expect the same result if I were to go out and take another sample. In fact, I have done that in the past. And indeed, that is the case. For change, I have multiple samples with in place kicking. With change, I have actually seen some situations where there was no longer sufficient evidence to say that indeed that is important. And that kind of matches what we're having with this p-value, that there's only marginal evidence. And that's why not just in place kicking, but just in science in general. That's why we do multiple studies. And especially if one study says, there might be something there, the next thing you should do is say, well, let's do another study. And when we do another study with place kicking, we find we don't have the same kinds of results exactly. Okay.
And why we keep elapsed in the model?
There's different ways to approach this. The ultimate goal for us is going to be prediction. That's what we're going to be talking about next year in terms of I want to predict success or failure. Generally speaking, there's not going to be that much of, let's say, a detrimental effect, if any at all, if we kept it in the model, because that's our goal in terms of our goals of prediction. Now, if you want to, and essentially what you're getting at is the whole concept of what's called model building or variable selection. And that's not our goals here. We're saying, okay, we have all these variables, let's just put them in there and see what happens. But if you're interested in forming, in regression analysis, we call it the most parsimonious model that best predicts the dependent variable. Parsimony means the smallest model. Then we would want to consider, do we actually need a lap 30 or not? And that is something that we would talk about in Study 75. Because in that course, we're very interested in interpretation. And you don't want to interpret a variable that's not important. Okay. So the ultimate, was there a question?
Yes. The base p-value, how do you use it?
The p-value
For the intercept.
Okay, you don't look at that one at all. Yeah, so don't pay attention to that. You can go back to, let's say, regular regression analysis to understand why do we still want to always have that intercept. Let's say if I have a regular old regression model, such as this, we can see that that intercept for the model is not 0. If I, naively said, oh, let's say maybe the p-value for another problem, p-value is large, and I'm going to take the intercept out of the model. What that means is then now you're forcing the model to go through the intercept, the 0, 0 point. And you don't ever want to force that to happen. Okay. So the whole purpose of what we've been doing is to get up to speed with being able to estimate a logistic regression model, understand some basics of it so that we can get to this point. And that is, we want to use a logistic regression model for prediction. I want to predict, should this observation, or let's say maybe a future observation, be categorized as a success or a failure? Y equal 1, Y equals 0. And so the first thing that we do just simply is, well, we calculate the estimated probability of success. So with the place-kicking data set for a particular distance, for a particular value of change, and so on, we just simply put those numerical values in for the x's. And then, given our beta hats, we do the math and we get a pi hat out. Now, based upon that pi hat, then, we can make a decision. Should I predict this to be a success, or should I predict it to be a failure? The most intuitive way to do this is, as you might expect, and we kind of discussed this before, is if the estimated probability of success is 0.5 or greater, how about we just predict that to be a success, Y equal 1. If it's less than 0.5, predict it to be a failure. So, make sure I said that right. If pi hat is greater than 0.5, predict it to be a success. If pi hat is less than 0.5, predict it to be a failure. That 0.5 is what's referred to as a cutoff probability, because we are essentially, that's our dividing line between success and failure. Now, you don't have to use 0.5 as the cutoff probability. You could use something else, 0.8, 0.2. And that's one of the big goals here for us to see what is the effect of that. Maybe you could have get a higher correct classification accuracy. Maybe you could do better, let's say, predicting Y equal 1 if I use, let's say, a pi hat of 0.2 versus 0.5. Maybe I could do better predicting Y equals 0 if I use a pi hat of 0.8 as my cutoff probability versus 0.5. And that's what we're going to be investigating. There's a tool that helps you do that called a receiver operating characteristic curve, or ROC curve, that we will be eventually getting into. But before we do that, we need to understand two things. We've kind of addressed before, but we just didn't use this terminology. We need to understand the sensitivity of a classification or prediction method, and also the specificity of one. And so what we're going to do is go back to our HIV testing, an example from the discriminant analysis section where we're talking about HIV testing. Hopefully this table looks familiar to you, where let's say we have a new diagnostic test to determine if someone is HIV positive or negative, meaning if they have it or if they don't. And so this new test is tried out, and we could, let's say, maybe form a contingency table of the corresponding results, where on the rows we have, is someone actually HIV, do they actually have HIV or not? So yes or no. And then we have the new test results. The HIV test, either you would be categorized as being negative or positive. Now we can see in this particular table there are places where we want to be, and then there's places that we don't want to be. So we want to have a correct, let's say, diagnosis. We don't want to have an error in our diagnosis. And so what's often done in medical, when trying out medical tests like this, and this is done in other applications outside of it, but it's easiest to talk about with respect to medical tests, is that people will look at what's called the sensitivity of the tests. And all that is a conditional probability. Given someone is actually positive, so it's a conditional probability, what's the probability that I predict or classify the person as positive? In this probability statement, perhaps I went a little bit too far here, but I put a little hat on top of it, because let's say if we have some observed data, we're coming up with a prediction. We're coming up with an estimation of this here. This is the sensitivity of a prediction method, a classification method, a sensitivity of a medical test. Do you want this to be high or do you want it to be low? High. Okay. Now note, so again, this is a conditional probability like you learned in your very first stat class, something like probability of A given B. This is not a joint probability, where in your first stat course, you learned about intersections, for example. It is not the probability you classify positive and you're actually positive. Rather, we're saying, okay, given that you're actually positive, what's the probability this test works? And says you are positive. Well, there's another thing that we are interested in, that is the specificity. And this just simply is the same thing as the sensitivity, but now we focus on the negatives, or HIV no. So, estimated probability you classify negative, given that you're actually negative. So let's say the clinical trial came back with the following results. Notice sometimes there was errors. So if we focus on HIV actual is yes. So we are in this row. We're conditioning on being in this row. Then 99 out of 100 times where we had somebody who actually had HIV, the test worked. So my sensitivity is 0.99. For the HIV no row, 195 times it got it right out of 200. So my specificity is 0.975. Now think about what we did in discriminant analysis, what we did with nearest neighbor classification. We were often forming tables like this, and we were looking at those proportions, remember? And so I just didn't call it sensitivity. I didn't call it specificity there. But I am now going to call it that. Why am I choosing this now? Is because this is these terms are often used now with logistic regression. And, and also, there isn't a nice way, there's not an exact way to extend this to the situation of, let's say if I have, let's say, 3 categories, 4 categories, you can't have sensitivity with respect to this or specificity with respect to this. Sensitivity and specificity is only used in the situation of where you have 2 possible groupings, 2 possible categories. So that's why I chose to do it now. Now we do see from this table, though, that we have some errors. Okay, and so we could express it in terms of the correct classification rate or correct prediction rate, as sensitivity and specificity does, or we could do it in terms of the errors. And so we could look at the false negative rate. Okay, simply probability that you classify as negative given that you're actually positive. And so in this particular case, let's see, I guess I didn't write it out. So this is just 1 minus the sensitivity. Why? Well, you remember what you learned in your first stat course. I can look at a complement. Depending upon your notation, you would say like probability of A is equal to 1 minus the probability of A complement, where the C means complement, or sometimes people will draw a bar on top of A. Well, I could also do exactly the same thing in terms of conditional probabilities too. Okay, so I just put a given B there. And that's essentially what we're doing here. Okay, so that's my false negative rate. We want this to be as small as possible. notice how, especially for HIV, this is a very important thing. Because if someone is actually diagnosed as negative when they're truly positive, and that means obviously they can't get treatment, they could also pass, unfortunately, the virus on to someone else unknowingly. Then there's also the false positive rate, which is just 1 minus the specificity. So again, just using conditional probabilities, using the complement, you have the probability to classify positive given actuals negative. We want that to be small. Okay, and I guess I did find what the false positive and false negative rate is based upon that table. Now, I put this in terms of HIV testing, but I added this stuff here in red, actually this whole thing in red, just to show you that in general, just to make sure that there was no misunderstandings, in general, on your rows you could put true, either it's a failure or a success, a 0 or a 1. And on the columns you have prediction, failure 0, success 1. Now, outside of this class, sometimes you will see people reverse the columns and the rows. So, in other words, put this up here, put this down here. There's not necessarily a standard. This is just what I chose to do here. So just be careful about that when you're maybe reading another paper or something else, doing something else outside this class. Now, before we get to an example that illustrates some of this, in application, one can change what that cutoff probability is so that it maybe increases the sensitivity or decreases the sensitivity. When you do that, if you, let's say, increase the sensitivity, it will, generally speaking, cause the specificity to go down. Vice versa as well. So if you change that cutoff probability to try to increase the specificity, it will cause the sensitivity to go down. So there's a give and take in terms of this. And so we'll look at these receiver operating characteristic curves will help you make a judgment about what is the effect. And then you can choose, and then you can decide, okay, I can live with a sensitivity of 0.9, or maybe I can go down to 0.8. What's the corresponding consequence with the specificity? Let me see if I want to talk about this. Here's a question for you. This is a hard question. If I want to increase the sensitivity, do you think I should make my cutoff probability higher or lower? Exactly, lower. Why?
Then you will have more positive qualitative identifier compared to your actual test.
Yeah, how about we put it this way? You're going to say more things are positive. And if you're saying more things are positive, you're going to catch these actual true positives more often. If that might be difficult to understand, think about the extreme situation of, let's say if I put a cutoff probability of 0.00001. Okay? So pretty much everything is going to be told to be positive. And so you're going to capture, probably almost all the positives in your data set. And so because of that, you're going to have a high sensitivity. But what's going to happen to the specificity? Go down, because you're going to be missing all the negatives. So that's something to think about always with this. Okay, so let's go to the example again. So for us, we have good equal 1, which is a success. We can think of it, if we want to go back to the HIV testing example, we can think of it as a positive. Good equals 0 is a failure. You can think of it as a negative with respect to the HIV testing situation. So the first thing that we need to know is, how can I get the estimated probability of success, let's say, automatically out from the R stuff that we just did? I'm sure you could program in the equation if you really wanted to and get pi hats. but there are easier ways to do that. The first way is that one of the components inside of mod.fit is something called fitted.values. So in a Stat 801 course, sometimes you will hear, let's say, for regular regression, your y-hats as being fitted values because you're fitting a line between the points. And this is essentially the prediction. And so that's where the name comes from. So for the very first observation in my data set, which is actually my training data, I have an estimated probability of success of 0.94. So if I use a cutoff probability of 0.5, I would predict that to be a success. There's a more general way that we will primarily use to do this, is that we can use the predict function. So if I say predict object equal, say where my model fit information is located, and then say, okay, I want to predict what kind of things do I want to predict? What's the type? I want to predict the response. In other words, essentially the probability of y is equal to 1 or y equals 0. Let's say I do that, and I put the results into an object called pi.hat because this actually gives me my pi hats. And we can see that for the first observation, indeed, I get exactly the same result as I had previously. And so we can see for the first 6 observations, they're all going to be predicted as successes if I use a cutoff probability of 0.5. Now, the reason why I like to use the predict function is because it allows us to predict things outside of my data set as well. And so I can now use my validation data set here. So again, I say predict object equal mod.fit, and then I can use an argument called new data and simply put in my validation data set there. I get my pi hats from that out. It's called pi.hat.v for lack of a better name. And we can see for the very first observation that in the validation data set, I have a high probability, so I would predict it as a success. Notice though, observation 3 in my validation data set will be predicted to be a failure. And since I have this open here, let's take a look at the validation data set. Did we actually predict it right? And in fact, we did. That third observation was actually a failure. Notice that that observation was a 51-yard place kick, so it's kind of long. And change was equal to 1, so it was done under pressure. So we like to be able to have, let's say, an automated way to make this prediction of success or failure. And this is where this if-else function that we've seen earlier in this class can come into play. So suppose I create an object called cutoff, for lack of a better name. We're going to make it 0.5. And if I say, if else, I want to test a condition. Is pi hat greater than the cutoff? If the answer is yes, assign it a value of 1, that particular observation. If it's not, I'll assign it a value of 0. I'm going to put that in put this into an object called pred.good, meaning I'm predicting is it good or not. I can do exactly the same thing with my validation data set as well. And then, let me just show you that indeed that did happen. So if I look at pred.good.v, here's all my 1s and 0s for those observations. So this if-else function works for every single value that you're passing into it for that test. Then I can go and use my summarize.class function that we first learned about in the discriminant analysis section, where I say summarize.class. Well, what was actually observed? Well, that's in the 9th column of place kick. That's my actual good variable. Then, for classify, what is my prediction for that good variable? Pred.good. And so if I run that segment of code, I get the same kind of summary as what we've seen before. Let me jump back over here to my Word document so I can write on it. So, for example, 1,249 times for my training data set, I predicted it to be a success, and it truly was. 13 times, although I predicted it to be a failure when it was a success. So because of that, then, my sensitivity, I can't spell sensitivity. Oh, jeez. I'm doing a blank here. Okay, sensitivity. Yeah. Okay. My sensitivity is 1249 over 1249 plus 13, which is 0.9897. My specificity, look how low that is. 0.11. What's my false positive rate? You have one of two different values to choose from now. What's my false positive rate? Yeah, 0.8896. My overall correct classification rate is about 89%. Okay. Let's look at it in terms of the validation data set. My sensitivity, my specificity, right there. And we can see we get similar results. My overall correct classification rate is 85% now. So now what I had done originally here, I just want to emphasize this, with my training data set, I was using resubstitution. We'll look at shortly how I can use cross-validation. Well, you might be wondering, well, what if we did choose a different cutoff probability? Okay, so let's say if I choose 0.7. So now remember what this is going to mean for us. It's going to be harder to predict something to be a success now because I have a higher threshold to pass. And indeed, that's what we see here. So I use the same code before, but I just say cutoff equal 0.7. So I don't give all the details here, but I use my summarize.class once again. Look at how my sensitivity now has gone down because I have that higher threshold. But look at that specificity now. Now it's 0.48, much higher than what it was before. My overall correct classification rate, though, it went down a little bit for resubstitution. Now with my validation data set, sensitivity is 0.88 now. But look at that specificity. It went up to 0.61. Overall correct classification rate is 0.844 here. So we have improvements with the specificity, but at a cost of a lower sensitivity. And while the place-kicking data set is not like an extremely life or death situation here, you can imagine, let's say now in a medical situation, where you're trying to make that judgment about, okay, can I live with a little bit of lower sensitivity so I can capture those true negatives better? Or vice versa. And those are the kinds of decisions that are often made with any kind of diagnostic test to determine if someone has a disease, to determine if, let's say, someone's cured, to determine if, let's say, some new treatment works. These are the kinds of decisions that are made, and that's why, as we will eventually get to, these receiver operating characteristic curves, which help us make this decision, are widely used. Okay, what about cross-validation? Well, what does this mean in this kind of a setting? So let's say, well, we would do it something like this. Go to your first observation, remove it from the data set, re-estimate the model, get its estimated probability of success, use that cutoff probability then to make a judgment of or prediction of success or failure. Then you put that first observation back in the data set. Now you take the second observation out and you do exactly the same thing. And you do this n different times for your your sample size event. So that means you have to estimate n different models. So with the place-taking data set, we have 1,425 observations. It means you have to estimate 1,425 different models. Okay? Here's a function that I wrote to do this, to help you out. Let's talk about what's inside of it. The function is called CV. Let's actually run the function first to see the results. So CV, my first argument is model, where I just simply put in, well, what are the normal formula argument that we would have for one of these models. And then I just have one other argument called data.set for the dataset name. Then what I'm going to do is save the results into save.cv. And let's see what we get in the end. It's going to take just a little bit of time, because I'm estimating 1,425 models. What I get is that now for each observation, what's its estimated probability of a success, where that observation was not used for estimating that model. So for that first observation, I get 0.943. Well, let's compare that to what we had previously for that first observation. 0.9434. So it's just about the same. Why is it just about the same? Well, one observation out of 1,425 isn't that much. And so, again, what we've seen before is that, resubstitution and cross-validation are going to be quite similar when you have a large sample size. But if you don't have a large sample size, you might also not be able to split your data, do a holdout data set. And so this is where this kind of a function can be very helpful to do cross-validation. Okay, so each of what's returned to us in save.cv is simply the estimated probability of success. So then I can use the same code as before, where I use my cutoff probability, let's say it's 0.5, and I come up with estimated predictions of success or failure, use my summarize.class function, and this is what I get. And as we would expect, again, we are getting similar results. So that's how you would do cross-validation. Let's briefly talk about the code here. Now, as a reminder of whenever you're faced with a new function and you want to understand exactly how it works, what you can do is go into the function itself and simply set the argument names. Set the argument names to what essentially, if you were to run the function, what they would be. So I'm going to set model to be this, data set to be this. And now I can just simply run the code that's inside the function. So n gets n row data.set. This just finds my sample size, number of rows. And then I need to initialize a vector for where I'm going to save the pi hats into. So we've seen this code before, numeric length equal n. And all that's going to do, let's try this again. Say errant comma. So what this is going to do is just initialize a vector that's going to be 1,425 long. It's just with zeros. And then I'm going to replace all those zeros next in a for loop, which estimates the models with n-1 observations, estimates the probability of success. So if I wanted to here, I could say R gets 1 in this for loop. So I'm just going to do it for the very first observation. So R gets 1, estimate the model. Notice how I remove that rth observation from the data set itself. I use that negative syntax that we've seen before. And then I use my predict function to predict just that rth observation. And I'm going to put that into the rth element of this vector that I'm saving. So if I run this, and if I just do head on pi.hat.cv, we can see what happened there. The estimated probability of success was put into the first element. I could do this as well for, let's say, R2. And now we can see the second one got there. And so this for loop then just repeats the process for all possible values of R, where R is the observation number. And I'm not going to run that because it's going to take a while. And then notice the very last line of the function. This is what I'm returning to the user from resulting with the function. All those pi halves. Okay. Any questions about that? Now we can also create some plots. Let me make this a little bit smaller. So remember what we've done before. We've got the principal component scores. And then we had the plotting point correspond to what was the prediction. And this is what happens when I do this here. Again, the black is a predicted success. Red is a predicted failure. And if you remember from when we did this in discriminant analysis, this is what we have for discriminant analysis for the same plot. And we saw how there was a definite, let's say, dividing line essentially there. And we talked about why that occurred with respect to discriminant analysis. Then when we saw this for nearest neighbor classification, we saw something that was quite different. We didn't have that strict dividing line. Now let's think of this now in terms of logistic regression. We don't have that strict dividing line, but it's closer, it's somewhere in between what discriminant analysis gave us and what nearest neighbor classification gave us. So I think that's kind of interesting. And generally speaking, I think of the logistic regression as somewhere in between in terms of how it makes those decisions. Yes?
But in logit analysis, you can set cutoff. You do different cutoff, you get different cutoff.
Exactly. And I think that might be coming up. Yeah. So this is for 0.7. So since I use 0.7, that means I'm going to have more failures predicted. And this is what I get. And so we can see that, well, we do kind of have a dividing line here, but it's not necessarily clear here. And notice how we kind of have it like that. Okay.
We have a standardized cutoff for everyone.
I mean, just in practice, what you use for standardized, in practice, is there a standard that people use? I would say 0.5 is used probably the most. But as I said, we'll get to these receiver operating characteristic curves, and that will help you make a judgment about, should I change it? And often what it comes down to is comparing the sensitivity to the specificity. You know, if maybe I feel as though a diagnostic method, think like a test for an infectious disease. If the sensitivity is not high enough, well, what I can do is lower that cutoff probability to increase that sensitivity. I'll just have to live with some of the false positives. In other words, live with a lower specificity. Okay. In the notes, I think I kind of had duplicated some stuff, and so that's why I ended up crossing some stuff out. Okay. Now, there's a term that I want to introduce to you that I don't think I have yet, and that is what's called a confusion matrix. First time I ever heard that term, I was confused. It was actually a student in this class, previous semester, who said, "Do you ever look at confusion matrices?" What? What are you talking about? And this is a term that computer scientists who also do stuff in this area came up with. And basically, all it is this table. I think it's the strangest term out there. And I never use it because of that. Statisticians don't use the term. All it is a table of your correct and incorrect classifications. Why don't we just refer to it that way? Wait, I just wanted to point that out because you might hear that term elsewhere. Okay. Let's discuss the project some more. Let's see here. So with respect to logistic regression, and I do want to come back to the nearest neighbor classification too, because there was something I wanted to discuss there. So for your data set for logistic regression, estimate and state the logistic regression model. Okay, that seems simple. Use the explanatory variables. I call them explanatory variables. They're a term I prefer. In this class, I've called them more independent variables. Use your independent variables in linear form only. That's what we actually did with the place kicking data. What I mean by that is, notice you don't have like a distance squared, or you don't have, if you've seen in another class, something called an interaction. I don't have a distance and wind interaction. So just the regular terms themselves. Just consider them that way. Then number 2, show me how the estimated probability of success can be found using the first observation in your data set. I actually want you to write out or type out the actual model, plug in the actual values for, let's say, x1, x2, and so on, and do the math. Show me what that estimated probability of success is, because it shows me you understand how to actually do the calculation. You don't necessarily have to rely completely on R alone to do this. Then, determine if this observation should be classified as a success or failure using a 0.5 cutoff probability, like what we just did. Number 3, using a cutoff probability of 0.5, summarize the classifications with the help of the CV function, what we just did. So use cross-validation. Tell me how everything worked out. Now I will make a decision now, given how much time is left. This 4 and 5, you don't need to do that for this project. We will talk about how to do 4 and 5 next time, but next time is also the same day that the project is due. This is still a very important topic here, what's in 4 and 5, and it can be on the tests, so just realize that. So I strongly recommend that you do it on your own, but you don't need to include it in the project. Okay, any questions about the logistic regression part here? Now with the nearest neighbor stuff, we had talked about 1 and 2 before, and I just didn't quite get to 3 through 5, and there's not much really to say here, but I do want to mention, because especially since I didn't like some of the wording that I had here. So again, on number 1, you're going to determine an appropriate value for k. How many nearest neighbors should you use? Number 2, with the k that you chose, I want you to summarize how well it did. Now, for number 3, though, state all that posterior, that's a word that somehow got put there. It shouldn't have been, because I had written the discriminant analysis stuff where we talked about posterior probabilities, and I accidentally used the same term. State all the probabilities to predict the grouping of the first observation using the results from part 2. So what that means is, let's say if you have 2 groups, okay? Remember what the knn.cv function will give you. It will give you the highest, let's say, probability for the grouping that actually occurred. So like 0.8. Well, what's then the grouping that it was not predicted into? 0.2. You need to tell me that. Now, if you have more than 2 groups, then it's going to become a little bit more complicated. Because now you need to give me the probability that it was for the grouping that it was chosen, but also the other 2 groupings as well. And so you may need to do some additional calculations on your own to figure out what those other probabilities are. So sorry if you have a data set that has more than 2 groups. The work that you're going to need to do might be a little bit more complicated. I've just given you some help here about, well, what would be possible functions that might be helpful to you. Then number 4, construct the same types of plots as what we did for discriminant analysis, and actually what we just talked about here too, where you have principal component scores, and show me the correct classifications, and also, show me how the predictions are done in terms of predicted predictions for the groups. Also, now compare that to did I actually have you do this? Yeah. So you're doing these two plots. So you need to do a plot for what was actually observed and then what was predicted. And then finally, number 5, summarize your results like this. And it would be interesting to see what it would be for logistic regression as well. But since some of you may not be having a binary set of groups, that's why I chose not to include a logistic regression in that table. But typically in actual practice, what one will do if you, let's say, have just 2 groups, is that you try a bunch of different methods and you look at a table like this to make a judgment about which is best. Okay. Any questions? So the next thing that we're going to be talking about is a receiver operating characteristic curve. And again, sorry to repeat myself, it's going to help you make a judgment about what should you use for a cutoff probability based upon, what you want for a sensitivity, what you want for a specificity. And all that a receiver operating characteristic curve is a plot. Wherefore, let's say for a cutoff probability of 0.1, find the sensitivity, find the 1 minus specificity, plot a point for it. Then for a cutoff probability of, let's say, 0.2, find the sensitivity, find the 1 minus specificity, plot a point for it. Do this for a bunch of cutoff probabilities, let's say from 0 to 1, maybe by 0.01. Then you connect all the dots with a line, and that's your curve, your receiver operating characteristic curve. And so as you can imagine then, that's going to help you see, okay, if I have a sensitivity of this is what I'm giving up in terms of my false positives. If I have a sensitivity of this, what am I giving up in terms of my false positives? And from that, then you can say, okay, well, I can live with that, so I'm going to choose a cutoff probability of 0.8. That's how it works. We are out of time, though, essentially. So we're not going to get to that today. We will next time. So just to look at, well, what's next in our class? Again, I'll have my usual office hours. Tuesday, we will hopefully finish up the logistic regression section. Let me see where we are at here. So we're on page 28. It's going to be close whether or not we will actually be able to finish it. I generally try to think about 20 to 25 pages of my notes for our class period. And we have about 20 pages left. Looking further ahead, project number 3, though, is due on that Tuesday at 5 p.m. Of course, then we don't have class on Thursday next week because of Thanksgiving. And then notice that we do have this test coming up. Actually, I just wrote my first draft of it on Tuesday. Test is Thursday, November 30th at 8 a.m. Okay, that is all here for today.